We're picking up where we left off from our notes in assignment 2.19, and we have discovered the power rule, and we've already determined that when we have the sum or difference of terms, we can do the derivative of each term separately. So here we could say the derivative of a difference is the difference of the derivatives. So our power rule tells us to multiply by the power and reduce the power by 1. Multiply by the power of 2 and reduce, so that our exponent would now be x to the first. And then we're asked to find f prime of 1. That would be the slope of the tangent at 1. So when we put 1 in here, we will get a slope of -2. All right, now we're going to go through the same process and see if we come up with the same thing for this function if we use our difference quotient. And when we have a binomial, be careful that you replace into both parts. You can do one or the other of your definitions of a derivative. I will try to quickly go through both here. So we'll start with this difference quotient. And I think I'll color code that second part here to make it a little easier for you to see which part I'm working on. So first, we have to do f at the binomial. So into each of the x's, we are putting in a binomial. So I'm going to put x plus h in for the x, and then I have to cube it, and I'm going to put x plus h for this x, and I'm going to have to square it. And then don't forget to do your minus f of x. So minus f of x would simply be the function with x as the variable. So make sure you don't forget both parts of the numerator. And now we can't do direct substitution until we can cancel this h here. We'd have 0 over 0 right now. So we need to stretch this all out. So we have to cube this binomial, and I hope you're a little familiar now with cubing binomials, so you might not even need that reminder from Pascal's triangle. I'm going to distribute this 2 right away this time so that I don't forget to do that. So first I would have 1 as the coefficient, x to the third, but then I'm going to double everything. And my second term would have a coefficient of 3, but I'm going to double it. And that would be a x squared h. And the next term would have a coefficient of 3, but it's multiplied by the 2, x h to the second. And our last term has a coefficient of 1, but it's doubled, so we'll do a 2h cubed. And then we have to square our binomial, so FOIL, and then I'm going to distribute -4 as well. So the middle term would be 2xh, but I'm multiplying it by -4. And then our last term would be a 4, but negative, distribute -4. And then with our second part, make sure you remember to distribute the subtraction sign. So I will have -2x cubed plus 4x squared, and all divided by h. And now take a good look. You will catch your mistakes if you forgot to distribute, because we are expecting this positive 2x cubed to cancel with this negative 2x cubed, and we are expecting this negative 4x squared to cancel with that positive 4x squared, so that all of our remaining terms have a factor of h. So now we're almost there. We simply factor the h out of the remaining terms of the numerator. So we'll have a 6x squared plus 6xh plus 2h squared minus 8x. And at this point, our 0 over 0 problem is taken care of when we cancel that h in the numerator and the denominator. And now we're ready to do the limit operator. The limit says let h go to 0. So this h goes to 0, and this h goes to 0. So these terms that have h's in them will drop out, and there we have it. Our remaining terms, 6x squared minus 8x, and that's what we were expecting when we did the power rule. So check it out again. Remember, we brought down the 3, so our first term became 6x squared. We brought down the 2, and our second term became negative 8x. So our power rule worked nicely. If we are asked to do the definition, that means that you have to go through the algebra process. And now let's do this definition using the alternate form. You would not have to do both, but you should be able to do either one of them. I should put f prime of x is equal to the limit as x goes to a of f of x minus f of a over x minus a. It's important that you remember the two difference quotients all through the year, even though most often in the future we're going to take the shortcut. All right, now let me not make the mistake of using our f prime. Let's remember what our original function was. We're actually using 2x cubed minus 4x squared. So make sure you don't mix up f prime with f of x. They're two different things. All right. So, and while I'm at it, let me do my color coding idea again here. Although it's not so necessary, I think this one looks a lot shorter. Our substitutions, first we simply do f of x, and we can see that that's 2x cubed minus 4x squared. And then we subtract, let me rid of that ribbon there. Then we want to subtract our f of a. So that would look like 2a cubed minus 4a squared. All right. All divided by x minus a. So you can tell, good reminder, we know that we need to be able to cancel this factor. And how are we going to be able to cancel? Only if we can group the numerator. So let's put these two terms together, and let's put these two terms together. So we'll do factoring by grouping. So I'll take a step here to rearrange. You might actually skip right to the next factoring step. But so everybody sees this, let me just reorganize. And then I'm going to put these two terms, 4x squared, and I'm going to go with red here. And don't forget we're distributing this negative, so this becomes plus 4a squared. All right, so now we've set it up so that we can factor the first two terms, the first pair of terms. First kind of factoring is to take out that GCF of 2, and then we would have x cubed minus a cubed. And we know how to factor the difference of cubes. So hopefully you'll remember all of your factoring rules. So there's the factor of the first two terms. And our second two terms, we can simply factor out a negative 4. So it will be a positive x squared minus an a squared. X squared minus a squared. So that will factor into these two conjugates. And some of you might just cross out those x minus a's. I'm actually going to take that out of the terms. So it's okay if you skip a couple steps along the way here. Just make sure you don't skip too much. So I'm pulling out the x minus a. So these are our leftovers. And now we've solved our 0 over 0 problem once we cancel. So now we're ready to do our limit operator. And our limit this time says let the x's go to a's. So each of these x's are going to become a's. Let x go to a. So when we do our limit, we will have an a squared plus an a times an a plus an a squared minus 4 times an a plus a. So notice what we've got here, 2 times 3a squared, so there's our 6a squared. And here we've got negative 4 times 2a, so there's our negative 8a. So this one we can write as f prime of a as our formula here. So both matched our difference quotient. All right, so let me rewrite our formula for f prime. Remember that the derivative of a function is a new function, and it tells us the slopes of the tangents at any point. So now we're going to use our derivative. We want to find the equation of the tangent when x is equal to 1. So we need two things. Our point of tangency. So we need to find out what is f of 1. So using our original function, make sure you don't mix up the two functions. Using our original function, here we get 2 minus 4. So our point of tangency is at 1, negative 2. And the slope of the tangent is simply f prime at 1. So we use our new f prime formula. F prime at 1 would be 6 times 1 squared minus 8 times 1. And that, by coincidence only, is also negative 2. That's the slope of our tangent. So the equation of our tangent is as simple now as point slope formula. So put in y coordinate from the point of tangency, put in the slope, put in the x coordinate. So subtracting here. So there's the equation of our tangent line. And in D, pretty simple if you remember the definition. A normal is perpendicular to the tangent. So no work involved here, really. We just use the opposite reciprocal. So the slope would be positive 1/2, but the point of tangency stays the same. Okay, new problem here. What about a negative exponent? Well, let's simply do the power rule the same. We bring down the power, and we reduce it by 1. So negative 3 reduce it by 1 is now negative 4. So another way that you might choose to write this is to put the x to the positive 4th in the denominator. So the power rule works with negative exponents as it does with positive exponents. All right, now let's work on the tangent. So what do we have? First, we should find out what f of 2 is using our original function. Our original function is raising it to the negative 3rd, so 1 over 2 cubed, or 1/8. So our point of tangency is 2 comma 1/8, and our slope is f prime of 2. So f prime of 2 would be negative 3/16. So I'll just slide over here so I have a little bit of room. So the equation of our tangent, y minus 1/8, is equal to negative 3/16 quantity x minus 2. And our normal is perpendicular to that. So our slope would become positive. You don't have to put a positive sign, of course. So if you know the equation of the tangent, you certainly know the equation of the normal. All right, let's see what we're doing here next. We are doing x to the 5th power, but we've got a vertical reflection. So we know the shape of this graph. Notice this is definitely a rectangular graph. Our vertical units are much smaller than horizontal. If we put 0 in, we know that 0 to the 5th is still 0. If we put in positive 1 to the 5th, but then we do the opposite. So at positive 1, we're going to get negative 1. And likewise, if we put in negative 1 to the 5th, that would be negative 1, but this negative, the opposite of that. So we've got our vertical flip. And if we put in 2, we would be expecting 2 to the 5th to be 32. But here we've got our vertical flip, so we'll go down here, and at -2, it will be rising. So we've got this flattening out in the center of our graph. All right, so let me label a couple of these points here. All right, and now let's use the power rule to find our derivative. We would bring the exponent of 5 down in front by multiplication, and we would reduce that power to 4. So let's find the slopes here are the derivatives. If we put -2 in for x, -2 to the 4th is +16 times -5 is -80. And because of the even exponent, we could right away fill in f prime of +2 is also going to be -80. F prime of -1 will be -5 times +1, and likewise +1 would do the same. And f prime of 0, of course 0 to the 4th power will be 0. Now let's look and see if that matches our graph. So this is probably the easy one. At 0, does it look like we have a horizontal tangent? If I can get that to stay on my graph, we'll try cheating a little bit here. So it looks like our graph has a horizontal tangent. At the 1s, does it look like our slopes are -5? Now remember that our graph is not square, so remember that you have to count a little differently. And at +2 and -2, does it look like our slope could be -80? Certainly our graph is almost vertical by that point. Okay, so why do our numeric derivatives are simply when you plug in numbers. Do they match what you expected at the graph? Yes, because it matches. We could say because f of x is decreasing everywhere. So we expected negative derivatives. Except at x equals 0, which has a horizontal tangent. And remember that this graph is always negative, always decreasing, that is, except at 0. So this point right here, you might hear us call it a saddle point. So it's not a turning point, but it still has a horizontal tangent. And that should do it.